Okay, so good morning, everybody. First, just to come back, yesterday I had a question by Philippe on what were those points. If you remember, so this is a diagram of pressure, temperature, and this is the pressure and temperature defined for cobalt and nickel if they extrapolate their scaling law from high pressure, high temperature experiments. And so those points are actually the pressure and temperature suggested by previous studies. And you can see that it's actually going up. I mean, it's a pity we don't see the year so much, but it's actually going up with time. So the more they can go to higher pressure, higher temperature in experiments, the more they find higher and pressure and temperature for the magma ocean as well, actually. So, but yeah, just to come back on that. The other point I wanted to correct indeed is that one. Yeah, it's indeed an impact on a fast spinning Earth. So to see that and make sure that we don't keep the wrong version. So that's a typical impactor on a fast spinning Earth. Impact on a fast spinning Earth. And you can see indeed like the Earth, which is spinning quite fast. And as you can see with those scenarios for the moon formation, they actually need quite small impactor. The size of the impactor is quite small compared to the standard moon forming impact scenario. So if I play it again, you will see the core merges really rapidly with the core of the Earth in that movie. It's really during the opening of the crater itself. Just to on that one, no. So that's a good question. When do they get re-impacting? And so that's something we started to do with Miki Nakajima, actually. One day we'll have the time to finish that study. There is nobody who actually has, characterized, the state of the core during those impacts in a regime diagram. So when do you get impact like that? When you get the impact I showed yesterday, where actually you had the re-impactor? It's not really clear. So. Okay, so let's switch to metal silicate differentiation. So I don't know if you remember, but yesterday we talked about the geochemical signature, and the conclusion was that to interpret the geochemical data, we need to have constraint on the degree of chemical equilibration between metal and silicates, right? So how are we going to get those constraints from the fluid mechanics? And so we need to study. I mean, this time I'm going to talk about that, so for perhaps like half an hour. So if you remember that diagram from yesterday, we concluded that basically the heating and the melting during the formation of the Earth is very much dependent on the size of the planet, of the growing object. And so it's very much dependent on the stage of accretion. For early stage of accretion, when you have planetesimals, melting will come from radioactivity, from short-lived isotopes. And for planetary embryos, it will come mainly from impacts. And so that means that the physics of metal silicate differentiation will also depend a lot on the size of the growing object and on the time, the stage in accretion. So if we start by planetesimals, so in early stages of accretion, the two different cases are going to, the key parameter is the time at which they formed. So if the planetesimals formed before 1 million years, they accumulated enough short-lived isotopes, aluminium-26 and iron-60, so that you will have enough heat from radioactivity to actually melt the entire planetesimal. It's an article by Heve and Stenders 2006. And if you melt the planetesimal, then core mental differentiation is quite straightforward. You start from an undifferentiated object, and that's going to melt, so you are going to have drops of iron that will just sink to the center of the planetesimal. And in that case, you expect quite efficient chemical equilibration. But now, if your planetesimal formed after about 2 million years, there is not enough short-lived isotopes to actually melt the silicates. So the silicates will stay solid. So you have a solid silicate matrix where you will have like pockets of iron or metal in it. The metal will more likely be liquid because you expect quite high temperature, but the silicates will be solid. And so the question here is, do you have percolation of the liquid metal within the solid matrix or not? And the key parameter to answer that question is whether the melt is connected or not. So here you have like two schematic representation. So if what we call the dihedral angle, actually I'm not sure in English, dihedral, nobody know, whatever. So if the angle, which is this angle, which is going to depend on like surface energy at the triple points here, if this angle is small enough, the pockets of melt here will be connected. But if it's too large, you will form pockets of melt that are not connected, and that's not going to percolate if you are in this stage. So the big question is, do you form connected melt or not? The short answer, I mean, it's a topic which is still quite debated. We don't have a final answer to that because those experiments are very difficult to do, especially at high pressure, high temperature. But the answer is yes, if there are conditions for that to be for that configuration to be the case, according to previous studies. If you have more than 5% volume of metal, you can form connected melt like that. If you are in very highly oxidized condition, you can also perhaps form that. And a more recent study show that you can also form connected pockets of melt if you are deforming your sample. So if, for instance, the solid matrix silicates are convecting, you will have some deformation over time, and that can help the melt to form connected pockets, connected what do you say, a réseau, network, thanks, of melt. Yes. I'm not sure I understand that, but that's really they find that in experiments, in high pressure and high temperature experiments. I'm not sure I understood that. Sorry? Is liquid because the temperature is high enough for the metal to be liquid probably during the stage. Yeah, so the melting temperature of metal is much lower than the melting temperature of silicates. So it melts much before silicates. And so if we assume that we have a connected melt, and then we can have percolation, here you have simulations that assume that you had a connected melt, and they have a matrix in black of undifferentiated material. They put an impact, on this matrix they have an impact, but the impact itself is enough to release enough heat to actually produce an instability which will cause an overturn or percolation of the entire undifferentiated matrix. And so you will form a differentiated body in actually a very short time, about 10,000 years in this simulation. So if you can have a connected melt, then differentiation of core and mantle in planetesimals is really fast. And so what that means is that more likely, most of the Earth's mass was formed from differentiated impactors. Another important point is, I was saying here, you do expect chemical equilibration because you are going to have very small droplets that are the size of the iron droplets in chondrites or in meteorites in a matrix of liquid silicates. But here it's actually not very clear. Do you have chemical equilibration during this stage? I don't know any study that has actually quantified that. So it's still an open question. Okay, so now that's it for planetesimals. Now if we go to the late stage of accretion, we have large impacts, most likely with differentiated impactors for the reason we just saw. So what are going to be, how does metal silicate differentiation work in that case? So those large impacts are very energetic, and so they release shock waves, and the shock waves can melt the impactor and a portion of the proto-Earth. And so just after the impact, you release the core of the impactor, which is liquid, in a pool of liquid silicates that we call the magma ocean, or the magma pool. And so because liquid metal is denser than silicates, it will sink in the magma ocean, and it can possibly form droplets, fragment into droplets of metal that will collect at the bottom of the magma ocean. And this stage is very important for chemical equilibration because you expect extremely turbulent conditions during those impacts. If you estimate the Reynolds number, which is a ratio between inertia and viscosity, you get Reynolds number larger than 10 to the 14th. It means that inertia is much larger than viscosity. And so you have very turbulent mixing between metal and silicates, and you can form, I was saying, droplets of metal. If you form droplets of metal, you increase the surface area between metal and silicates, and so you favor chemical transfer. So those processes really govern metal-silicate equilibration, and so the composition of the core and the mantle. But also, if we want to understand the interpretation of geochemical data, we need to better understand the degree of equilibration during this stage. So how do we study this stage? So as we saw yesterday, we can study large impacts using simulations, numerical simulations, impact simulations, as the one you have here. And we saw that, so those simulations show that those processes happen in about a few hours, as we saw yesterday. However, there is one main limitation with those simulations, because the smallest scales in those simulations are of the order of 100 kilometers. As we saw yesterday, chemical equilibration is going to be efficient on a length scale of about 1 millimeter, or at least smaller than 1 centimeter, the typical length scale that you find for chemical diffusion in a few hours. And so there is no way the simulation can say something quantitative about chemical equilibration. So we have to do something else. Something that has been done, and it's quite a new topic, I must say. So it's a topic that has been perhaps studied for the last 10 or 15 years. The first that studied that topic were perhaps Ishikawa et al. 2010 and Ruby as well. Dave Ruby in 2003 did a paper on that. And the view that we had is that you form a rain of metal drops in the magma ocean, and each of those drops equilibrate with the magma ocean, or in the magma ocean. And what those studies have found is that you need droplets with a size of less than 1 centimeter if you want efficient chemical equilibration. However, again, in those simulations, they include size, so they really focus on this 1 centimeter size. And the size of that box is perhaps 10 centimeter, but they are completely missing the large scale as well. So there is, again, something that is missing. And one question then that is not resolved by those simulations is actually, do you fragment the core of the impactor into those centimeter size drops? And how long does it take? So what is missing to study that process is turbulence, because turbulence is going to is what you need to actually couple the large scale with the small scales. And it's very difficult to produce fully developed turbulence in simulations, and that's why experiments, so lab experiments, are very useful to study that topic, because you can produce turbulence much more easily in experiments. And there has been a number, actually, in the fluid mechanics community, there have been a number of studies on the fragmentation of a liquid, and a number of experiments on the fragmentation of a liquid in air, in turbulent conditions. And so here you have a typical sequence of a fragmentation event, where you have a drop that first deform, as you can see here. It flattens into a pancake shape. And then it starts to destabilize and form filamentary structures that you can see here. And the filamentary structures destabilize themselves and form drops. And when you study that kind of process, the main control parameter is perhaps the Weber number. The Weber number is a ratio between inertia and surface tension. So physically we understand why, because inertia is what's going to deform your drop, But surface tension is what wants to make the drop spherical, right? Surface tension wants to minimize the surface energy. So a sphere is what minimizes the surface area, sorry. Okay? If you apply that for core formation, you find Weber number of larger than 10 to the 12. So we are looking at a process where inertia is really large compared to surface tension, and that's why we think that we can fragment into drops. So, however, most of the experiments that have been done so far have been done in air, as this one. And so what we want to do is to do an experiment when you have fragmentation of a liquid in another immiscible liquid, because it's more relevant for metal silicate differentiation. So here is the experiment that we have developed a few years ago with some colleagues of mine. So Renaud Deguin and Peter Olson. We did those experiments in Hopkins in Baltimore in the US. So here you see that okay, if I stop here, basically we release in blue a solution, which is a water-based solution in silicon oil, which is an immiscible liquid. And so you see that the initial object falls, start to deform and destabilize, and eventually form this rain of drops here. So this regime is very much similar to the rain regime that I showed earlier, or that simulation found so far. And that's a regime that we found a quite low Weber number. Now, if we go to higher Weber number in our experiments, we find that regime. So it's going quite fast. It's real time. So I'm going to play it a few times. I should have put it on repeat. So what you see is that now you have droplets that are very small compared to the size of the system. You actually barely see them on this movie, but you see that they are almost of the size of the pixels in that movie. And you see that you have a regime that is much different from the rain regime I showed you earlier. Now you have this plume, turbulent plume that goes down, and the released liquid fragments to drop into this turbulent plume. And so we think this is a regime which is relevant for core mental differentiation after large impacts, not the rain regime so much. I don't know what happened. Okay, so here you have pictures of the same regime with a better resolution. So you see the objects that form this plume, and the plume fragments into droplets between those two pictures. And at the end, you get this cloud of droplets here that you see here. And you see that the breakup into drops, so if you look at this picture, you see that the released liquid has not fragmented yet. Or actually here, no, it has fragmented here. We see droplets. So here it has fragmented, but if you go back in time with a distance of about 1 diameter of this cloud, you see that the liquid here is not fragmented at all. So you have a fragmentation into drops, so breakup, we call that breakup into drops. That is a very sudden event, and that happened in the entire volume of the cloud, which is quite a new regime actually that has not been observed before. So what we did is that we measured this, because the breakup happens so rapidly, you can measure the breakup length, which is the length at which, or the distance from the source at which the breakup occurs, breakup into drops occurs. And we did that in all our experiments, and we find that the breakup length, the distance at which breakup occurs, decreases with the Weber number, and it tends towards a constant value, or at least we can say that we don't see significant variation in this region when we are in the turbulent regime. And it's quite intuitive. The more inertia you get, the faster the fragmentation. And so, of course, so here we are several orders of magnitude from the real system. So it's quite difficult to extrapolate that directly, especially because I say it's constant, the results are more or less constant here, but basically we don't have enough data to see that we don't just have a little bit of dependency with the Weber number. But if you play the game of extrapolated that to the Earth, you find that the impactor core fragments after a fall of about 4 to 8 initial radii, which is really quick. That means that most impacts have the time to fragment to drops, except perhaps for the largest giant impacts. But after most impact, you have time to form drops of metal. Okay, so, but it's not enough to have chemical equilibration, because for that to be enough, you need the drops to be small enough. So what are the size of those drops? So in the literature, you actually find theories for fragmentation in a turbulent flow. And those theories predict that the drop size evolves as a Weber number to the -3/5. It's basically a scaling that you find if you, I know if you heard of Kolmogorov cascade. Well, for those who know what is Kolmogorov cascade, basically it's like you do the same reasoning but with surface tension, so the cutoff length is not viscosity but it's surface tension, and you find that scaling. So if you apply that scaling, you find that the drop size should be about 1 to 2 millimeters in those experiments, if you take the Weber number of the experiments. And it's quite, I mean, it does agree with the size we find in the experiments. Now, if you apply that to metal silicate differentiation, you find drops that are smaller than 1 centimeter. So according to previous studies, that's enough to have full chemical equilibration of the droplets. So the drops of metal you form will likely have time to equilibrate fully. However, they will equilibrate, but only within this cloud of material, right? So they will equilibrate only with the silicates that are entrained within this cloud of drops. So what that means is that the really key parameter that's going to govern chemical equilibration is the amount of silicates that you entrained within this cloud. And the nice thing about that, so we are going to talk about that in the next lecture actually, but you can develop a theoretical model that predicts the amount of entrainment of silicates within this cloud. And this model tells you that the volume of entrained silicates is just a function of the magma ocean depth. So that's very nice, because now you can define the degree of chemical equilibration as the mass of a given element exchanged between metal and silicates, divided by the maximum mass exchanged if the metal and the silicates were at thermodynamic equilibrium. So if basically the composition were equal to the partition coefficient. And if you define it like that, you can show that the degree of equilibration then is just a function that looks like that of the entrained volume of silicates with d the partition coefficient. So the key message to get from that is that we think that the key parameter that governs chemical equilibration is actually the amount of silicates that equilibrate with metal. And that's not the view that is the most, that was the most common at that time when we concluded that. So it's important to have that in mind. And so then, now you have a law. Basically, you can inject this into there, and you can predict the degree of equilibration as a function of the magma ocean depth. For instance, if you take the black curve, here it's for a partition coefficient of 30, which is the partition coefficient that we use for that is used for hafnium tungsten in general. And you can see that if you have an impact with an impactor 10 times, or if the magma ocean is, sorry, I should actually have, no, yeah, actually, yeah, okay. I should have switched that scale. No, but it's true. Okay, so if the magma ocean depth normalized by the impactor size, or if the magma ocean depth is small compared to the impactor size, then you have a small amount of equilibration. But now if the magma ocean depth is very large compared to the impactor size, you actually have a degree of equilibration of 1, meaning that you are almost full equilibration. Yeah. Yes. 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 But you can do the same. Yeah. Here yeah, that's true. It's for tungsten. But yeah. But my point is it's just an illustration. Is like whatever the partition coefficient, you can predict the degree of equilibration No, but you won't migrate into the core anyway. Yes. Yeah, yeah, I should, yeah. That. So the amount of, if you have a single element, so let's say a tungsten, which you have an equilibration between the metal within the magma ocean. If you had full equilibration, the composition of the magma ocean and the metal will be such that their ratio, the composition of tungsten in the metal to composition of tungsten in the magma ocean should be equal to the partition coefficient. So it's basically the discrepancy from that, because here you equilibrate with only a portion of silicates and not the full magma ocean. So you don't have as much equilibration as you would get if the entire magma ocean or the entire metal equilibrated with the metal. Yes. 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 Yeah, but what matters is the volume of silicates you entrain compared to the volume of metal. No, so yeah, it is because I was saying it's if you take the really a given element that is exchanged between those two, how much mass is exchanged between metal and silicates. And if you have a large enough volume of silicates, you actually have a mass exchange that tends towards the value you would get if it was equilibrated with the entire magma ocean. You can show that. Yeah, I can. We can look at the derivation together, but yes. No, but then you can mix with the metal that saw the metal earlier. Yes. No, I was saying if you write the equation, the key parameter is actually the volume of silicates divided by the volume of metal of the impactor core. So if this value um, is very large, tends towards infinity, you actually have a degree of equilibration that tends towards 1. So of course I agree with you, there will be a tiny difference, but you can show that the difference will be actually small. So yeah, we can look at the formula together later. But the key message to remember is that, is that basically you can predict the degree of equilibration if you give a magma ocean depth. And those scalings are now being used in geochemical models of Earth formation. So, okay, but now your metal collects at the bottom of the magma ocean. What happens next? So it's going to then migrate into the matrix, into the solid mantle, and it can migrate as a form of diapirs, for instance, within the solid mantle. So what are the length scale and time scale for that? So the typical length scale is actually larger than 1 kilometer. And the time scale is quick, but not as quick as in the liquid magma ocean, so a few years, perhaps up to 100 years. And so the typical length scale for that process, if you can compute the typical length scale you will need for efficient equilibration, you find something of about 1 meter in this time scale. And 1 meter is much smaller than the size of those diapirs. So you don't expect chemical equilibration during this stage. However, can you have chemical transfers? Because chemical transfer, the diffusion of temperature is much higher than the diffusion or the diffusion coefficient of thermal coefficient diffusion is much larger than the diffusion of compositional elements. So can you have chemical transfers? So there are a number of studies that investigated those processes. So basically the migration of liquid metal in the solid mantle. And the answer, first the answer is that we don't really know well the fluid mechanics of that, especially we don't know whether you will form diapirs or dikes. If the mantle is not so much viscous at this stage, you expect to form diapirs as here. So large-scale diapir of metal that migrate in the magma ocean, in the solid mantle. But if the mantle viscosity is large, so if the viscosity contrast between the metal and the mantle is large, then you would expect to form dikes, as this one where they have they inject some liquid into an agar gel, so like something like gelatin, and they see the formation of this dike. So the key question is, do you form diapir or dikes during core mantle differentiation? We don't really know the answer to that, mainly because it's really difficult to know what was the mantle viscosity at that point, at that time. But those two regimes are quite important. It's quite important to know which regime is relevant, because if you form a diapir like that, you actually have much deformation in the solid mantle, because you see that the mantle around has to flow around the diapir. So you will have viscous dissipation in the solid. And so that means that you will hit the solid mantle here. But if you are in this regime, you have quite small deformation in the solid mantle now. And most of the deformation and the viscous dissipation will be in the dike. And so you will hit the metal in that case. And that's really important. You want to know the initial condition, the initial temperature of the core and the mantle. Especially for the core thermal evolution model now, we need the core to be very hot at the beginning. Is that realistic? So to answer that question, one would need to really quantify those effects. And I don't think they have been fully quantified so far. Okay, so to summarize on this first lecture, we saw that Earth formation is a topic that really requires interaction between geochemistry and physics, both astrophysics, geophysics, and mineral physics. So it's really now, I mean, the next steps are really to couple those fields together in a wise way. There are a number of studies that did that. I mean, they started to do that already. The other message is that you have a really wide range of length scale and time scales. And again, the game now is to be able to couple those scales by integrating, for instance, parametrization of the small scale into the large scales. Some open questions on Earth formation. So we saw a number of them. The first one, we don't fully know how to go from dust to kilometer-sized planetesimals. There are models, but they are not completely convincing, or let's say they are not very parsimonious so far. So it would be good to find models that are more parsimonious and that explain the formation of kilometer-sized planetesimals. Moon formation, it would be good to have a single scenario that explains both the angular momentum of the Earth and the Moon and the compositions of the Earth and the Moon. The scenario that has been proposed recently, the one we talked like about the synestia, might answer that question, but I think it's a very novel scenario. I don't think we understand very well the physics of this scenario so far, so it's not a completely resolved question, I would say. Core mantle differentiation, we don't know the degree of chemical equilibration if you have percolation in planetesimals. And that's really important because when you have then large impacts, you want to know the initial condition for the impactor. So you need to know the composition of the impactor, of the core and the mantle of the impactor. Now in the solid mantle, we don't know if you will form diapirs or dikes, and that will be important this time for the temperature of the core and the mantle. And a last topic that I think Mathieu will probably talk about this afternoon or tomorrow, is the origin of, so now you have geochemical data, or I should say isotopic data, that observe heterogeneities in the mantle that have to be primordial, or at least form at least within the 500 million years of the Earth, depending on what scenarios you consider. 50 if it's magma ocean, yeah. Yeah, but yeah, at least 500 million years, it's like an upper one, right? Yeah, but yeah, and probably actually within the first 50 million years of the Earth. And so that's really quick. That means that you need heterogeneities in composition in the mantle and in the magma ocean, within 50 million years, because the last giant impact, the moon forming impact, is thought to have occurred actually after 50 million years. So how do you preserve heterogeneities in the mantle after a giant impact? So I think those questions are not resolved yet either. And here you have a few references if you are interested in this topic, of like a few reviews and good books on the topics. That one is really a good book, and those two are basically reviews on the topic. So that's it for this for the Earth accretion part. So any question on this first lecture? Yes. Is what? Ah, okay, we can do that. It's not going to be I mean, it's basically it's the order of magnitude that you need to resolve in the flow if you want to. It's just it was more an order of magnitude, but the way I computed that is that. So we saw that it's efficient if you have a length scale of 1 centimeter. So the time scale, you can take delta divided by u relevant as its length scale. If you assume a Kolmogorov cascade, turbulent cascade, u delta is evolves as u at the large scale times delta over d, the largest scale. So let's say I have my impactor here, which has a diameter d, and the impactor fragments into droplets. But I take the large scale d in that scaling to the power 1/3. And you can just inject that there, and you find milliseconds. U0, so your delta cancels basically, so you have a 2/3 here, 1/3 there. So that time scale gives you a few milliseconds. What do you mean? Yeah, so I take kind of so first it's an order of magnitude. You can also have smaller droplets actually. So just an order of magnitude because we saw that the characteristic time scale to have equilibration is 1 centimeter, so that's what you would find. Just to give you an idea that you need to resolve the flow on very different time scales if you want to get an idea of the dynamics. I'm not saying that this is the answer. It's really more an order of magnitude to realize that you have a really wide range of timescales. Does that answer your question? Yeah. What? Yeah, so that's yeah, so I didn't have time to mention that, but yeah, so kind of what I wanted to make. So here I assume that you have coalescence of droplets. The drops fall in the magma ocean, you have coalescence of droplets. Basically in those studies, they assume that here it's basically all the droplets that coalesces and form liquid. But in those experiments, they also assume, like actually those experiments are the case where you didn't have time to separate the drops from the liquid. It's really not clear how long it takes to separate the two liquids when they have formed a layer of drops here. There is a paper by Sumita on that, but it's very difficult to extrapolate it to what are the relevant parameters for metal silicate differentiation. How does it take to reseparate the metal and the silicate at this time? But that's an important point because if you actually entrain here an emulsion of metal and silicates, that means that you entrain in the deep mantle, you entrain some of the magma ocean as well. And that kind of affects the dynamics of the mantle after that. Yeah. Yeah, exactly. It mixes the mantle, and it can. So what they show in this study is that it can. You bring material that is going to be lighter than the solid mantle, and you can form plumes on a much longer time scale that will go up and form like volcanic eruptions at the surface. Yeah, so that's an important question. Yes. Any other question? Nope. Okay. So let's go to the second lecture then. So we are going to see actually a bit more of those processes that we just discussed, but in a bit, I mean, in another point of view, because from the point of view of dimensional analysis. So I thought it would be good to introduce a bit of that. So the problem is that for the people who know about it, it's going to be a bit boring. But I think it can be very useful for people who haven't really seen dimensional analysis that way. And so that it's not too boring for the people who know about it, we can like have a number of exercises so that you can try to play with numbers and order of magnitude. So I was saying at the beginning, dimensional analysis is just, it's really important in earth sciences and in the in geodynamics, because it's really the way, I mean, the question is, how do you build an experiment or numerical simulations that will say something about the Earth, and how do you extrapolate your results to the Earth and to the deep Earth? And that really relies on dimensional analysis. So we basically, when you study the deep Earth, so either the present-day deep Earth or the deep Earth in the past, you face processes that are basically all the surface processes. For instance, the magnetic field is due to flow motion in the outer core. Plate tectonics is related to mantle convection. And we saw already in the early years that fluid mechanics is also very important. So the dynamics of the Earth is really much dictated by fluid mechanics. And so, as I was saying, how do you build experiments and simulations that are going to say something about the deep Earth? So first concept, which is very important, we saw a bit of it in the previous lecture, is dimensionless numbers. So dimensionless number is just a ratio of two forces or two energies or two time scales, two length scales in the system. So it's a number that has no dimension, which is basically the ratio of two numbers that have the same dimensions. Okay. So one example that we saw already is the Reynolds number, which is a ratio between inertia and viscosity. And you can also write it as a ratio of the viscous time scale to the advective time scale. And it's equal to UL over nu. So is that completely obvious for everybody, or should I write that, how you write the viscous time scale and the advective time scale? No? Everybody's okay with that? Okay. So plumes, so let's take an example to illustrate why those dimensionless numbers are important. So for instance, let's take the example of plumes. So a plume, so that's why I brought that. We'll see if that kind of experiments never work. It's just so that you see, I mean, you see plumes all the time around you. Does somebody has a pen that they could borrow without destroying? No. Yeah, whatever. Or perhaps I will do it at the end if I have time then. But everybody has seen a plume before, right? So plumes, it's basically you get a plume when you inject a material here less dense in a matrix, which is so basically if you have an ambient flow here, you inject something which is lighter, you will form a plume, and we encounter them in very different geophysical systems because you have plume in the mantle. Probably you heard about it last week. For instance, here it's like the volcanism in hotspot volcanism is thought to be due to a plume rising from the core mantle boundary. So hot material rising in the solid mantle. In the core, so here you have a simulation of core convection, and you actually in these simulations you see actually you form many plumes that rise from the inner core boundary to the core mantle boundary. And you find them at the surface as well, because here you have an example of hydrothermal plumes, volcanic plumes. If you use incense or if you smoke, you probably saw plumes before, right? So you find them everywhere in nature. So why is it? So let's apply that to this concept of dimensionless analysis to plumes. So the Reynolds number of the plume is going to be the velocity of the plume times L, which is the typical width of your plume, divided by the viscosity. And here are two experiments that are done at very different Reynolds numbers, but quite similar configurations. So here, basically, they inject a buoyancy flux of temperature, so they heat a portion of the tank at the bottom in a very viscous fluid. I think it's a glucose solution, and they see a plume rising. So the ISO lines are ISO temperature that they visualize using liquid crystals. And you see that you form a plumes, which is very laminar. If you follow the contours here, you have very smooth ISO temperature contours, right? And these plumes is at actually quite low Reynolds number. So when you have a very low Reynolds number, viscosity is very important, and you have those very smooth laminar plumes. Now, if you go to much higher Reynolds number, for instance, as this one, you see that you form a plume which has a morphology very different to that one, right? So now you have a flow which is very much turbulent in the sense that you produce a lot of length scales. So just to go, perhaps as an illustration, so yeah, so that's another visualization of a turbulent plume. I quite like that one, actually. You just put a light sheet in the plume, and the plume contains fluorescent dye. So what you visualize is really the flow inside, in a cross-section of the plume. And you really see that there are many, many length scales here. So that's why we say that the plume is turbulent. And yeah, so my point was really that the Reynolds number, as we saw, is really going to govern the morphology of that particular flow. And now if we come back to the geophysical configurations, if you take a mantle plume, let's take velocity of the order of perhaps 1 centimeter per year, viscosity of 10 to the 18 meters squared per second, and a length scale of about 100 to 1,000 kilometers, you find Reynolds number of the order of 10 to the minus 22. So it's extremely low. And so if you want to study plumes in the mantle, you need to take, build experiments that will be in this laminar regime. So you need to make sure that your Reynolds number will be small compared to 1. So those laminar plumes are the ones that are going to be relevant for the plumes in the mantle. And now for the core, if we do the same exercise and we take velocity of 5 times 10 to the minus 4 meter per second, which is a velocity that the order of magnitude you get from inversion of the geomagnetic field, so the flow at the top of the core, a viscosity of 10 to the minus 7 meters squared per second, and a length scale of 1,000 kilometers, you find a Reynolds number of 10 to the 9. So this is really, really high, right? So this is going to be a very turbulent flow. And so if you want to study the flow in the core, you need to study, look at turbulent experiments at large Reynolds number. Okay, so let's try to apply that. So there are other dimensionless numbers that are relevant for the core and the mantle. Can you, it's up to you. Do you want to play the game? So the game is like, can you write different dimensionless numbers that are relevant for the core and the mantle and estimate their order of magnitudes? And conclude about what are the relevant forces for both the core and the mantle. So what ingredients you need to inject in a simulation and an experiment if you want to study convection in the mantle or convection in the core. So same as yesterday, if you want to do that by yourself or with someone like a neighbor, 1 or 2 people, perhaps 5 minutes. Is that something you want to try, or is that something which is completely obvious for everybody? Philippe, I expect it's obvious for you. Yeah? Okay, so you can try. So what are the other dimensionless numbers that are relevant? not to be the case. Going to reset. Okay, any ideas? Did you do anything? Sorry? Yes. So if you write them, yes. Which one did you? So can you try to write them in terms of timescale and? Yeah, but my point here is like, yeah. So if you just convince you of that it's not doesn't play a role. So if you want to convince you that it doesn't play a role, you want to estimate it and say, okay, it's really small, and it's really large, and so I don't. Just to make the game is just to do. You know where it's coming from. You know to convince yourself that. Okay, so should we? Any ideas? What are the? So what is the first number that will? Do you have any suggestion of the first number to look at? Really? Yes. So how do you write it? I mean, what is the R? What does it represent? Hmm? Yeah, convection, but in terms of timescales, since we say that. So we said that the dimensionless numbers are ratios of different timescales. So what would be the timescale that are relevant for the Rayleigh number? Ratios of what timescales? Hmm? Sorry? Yeah. But ratios of what are the definition of? I mean, if I want to write the definition of it, and you want to write the Rayleigh number as a ratios of different timescales, what timescale do I scale? Yes. Yes. And diffusion. So in the classical definition, usually it's we take like the definition of viscosity, or so the time scale for viscous diffusion times the time scale for thermal diffusion divided by the time scale for advection squared. And so the time scale for viscous diffusion so you can take if D is a length scale, except that it's the ratio of that. No, what am I saying? The opposite. D squared. That gives you a time scale. So the length scale squared divided by the viscosity. And same for the thermal time scale, but with thermal coefficient, diffusion coefficient. And if you inject that, and for advection, what time scale can you take? So perhaps D over U, if U is a characteristic velocity. Does that make sense? And the characteristic velocity, if you define it as square root of alpha delta t g d, because so what is going to drive convection in this case? Buoyancy, yes, buoyancy. So the typical, just by dimension analysis, if you want to form a length scale, a velocity scale with buoyancy, you get that the kind of the first estimation you can get. Okay, so if you want an order of magnitude. So if you now inject that in there, you find that the definition of the Rayleigh number is this. But my point is just I wanted to make just to really emphasize that this is not coming out of nowhere. It has some physical meanings. Okay. So the Rayleigh number in the mantle and the core, do you have estimations, or? I guess it's not so completely tricky, easy. So if you take a delta T in the mantle of perhaps 1500 Kelvin and thermal diffusion of perhaps 10 to the minus 6 meters squared per second, you end up with a Rayleigh number of the order of 10 to the 7, but I mean it's really an order of magnitude. So that's the Rayleigh number in the mantle. So you see it's quite big, so buoyancy is quite important compared to diffusion. So you are going to have efficient convection, quite powerful convection. Now in the core it's a bit more tricky because but if you apply that for the core and you take instead you take a delta rho or delta T of the order of millikelvin, which is a temperature difference associated with convection we expect in the core, you find a Rayleigh number of the order of 7 to the times 10 to the 23. So quite much higher actually, right? So you can see that buoyancy is even more important in the core. So what other dimensionless numbers? And it could be, it doesn't have to be, you don't have to give me a name, just in terms of, okay, what are the time scale? What are the different time scales that are relevant for core and mantle or processes? Yes, which is? Yeah, I didn't hear the beginning, but yeah, it's viscosity over the Coriolis, yes? So this is an omega rotation rate. So time scale of rotation divided by viscosity, because you have a viscous time, but you also have rotation time, right? The Earth is rotating. So if you apply that to the outer core, you find, as we heard yesterday, an Ekman number of about 10 to the minus 15. So that means that viscosity is really not important compared to rotation. So rotation is very much important in the outer core. If you do the game in the mantle, you find an Ekman number of the order of 10 to the 9th. And that's mainly because the viscosity in the mantle is much higher, right? So that tells you that viscosity is going to be much more important than rotation in the mantle. And that's why rotation doesn't matter for mantle convection, okay? So yeah, again, it's just so that you know where it's coming from. What other timescales? Well, actually, those two timescales, they are already we already have them. So you could take the ratio of those two timescales. That's what we call the Prandtl number. And again, it's quite different in the outer core and in the mantle. In the outer core, it's not completely well known, but let's say between 10 to the minus 3 to 1. And in the mantle, it's much higher again. It's 10 to the 24, perhaps. Given that we don't know very well the viscosity of the mantle, it's plus or minus 2 order of magnitudes. But just to give you the idea that in the mantle, again, viscosity is much stronger than thermal diffusion. So any convection in the mantle is a convection where the velocity, the momentum, diffuses much faster than temperature. So it does change the flow, the morphology of the flow as well. Yeah, I guess that's about it. But the conclusion on that is that, so if I... It's just to illustrate how you can get from dimensional analysis and dimensional numbers what are the relevant forces in your system. What are the forces, what are the ingredients you need to include in your given simulation or experiments to model the geophysical model system you want to model, okay? If you want to model convection in the mantle, you need obviously viscosity, as we saw, and you need buoyancy because the Rayleigh number is very high. If you want to model convection in the core, we saw that you need rotation, you need buoyancy, and you probably need inertia as well. Lorentz force, yeah, so I haven't talked about that, but you probably hear about it by Philippe later on.